Hello everybody, we are just discussing today thermodynamics, one of the important most topics of heat. I am Srinivasa Charyulu. Thermodynamics, while discussing this topic, one should remember three very important areas. One is the concept of Joule's law. This Joule's law, which gives us the relation between work done and heat energy thereby generated in the system. So if you take W is proportional to energy of heat produced. Work done on any system is directly proportional to the quantity of heat generated in the system, like we people used to say or take this particular statement like that. W can be written as J times H, where J is called either mechanical equivalent of heat, you can call that, otherwise it is also called as Joule's constant. In fact, we know its value as 4.186 Joule per calorie. But for all practical calculations, we take this value as 4.2 Joule per calorie. And remember carefully, in pure SI units, the value of J will be taken as simply 1. So its applications are to be discussed. That is first zone of this thermodynamics topic. In fact, thermodynamics has been developed just by taking this concept only. So that is one area one should remember before taking up the applications. And coming to the second part of it, the actual part of thermodynamics, in the sense what is zeroth law of thermodynamics. When A and B are in thermal equilibrium with each other, and A and C are also in thermal equilibrium with each other, then one can understand that B and C are also will be in thermal equilibrium with each other. This is the statement what we used to call it as zeroth law of thermodynamics. Exactly in the same manner, what is the first law of thermodynamics? The quantity of heat energy that has been supplied to a system, that is dQ, is the sum of the change in internal energy of the system and the amount of work that has been done in that particular process. So dQ is equal to du plus dW, we people used to write. The same, of course, we can write it as NCP dt is equal to NCV dt plus NR dt. This is the way of rewriting the same equation as such. N refers to the number of moles, Cp refers to the specific heat of the gas at constant pressure, and Cv represents the specific heat of the same gas at constant volume. R is of course universal gas constant. In fact, it is this equation which yields you the result Cp minus Cv is equal to R. So these are the concepts of first law of thermodynamics one should remember. So this is one zone we have to go for. And coming to the next one, what exactly are the different processes we have and how to take this first law of thermodynamics in each of the processes as such. For example, when you take dQ is equal to du plus dW equation, then by convention we people used to take dQ, du and dW respectively. One example I will give you. If suppose heat is supplied to the system, or in other words, heat is taken from the external source by the system, then we people used to write dQ as a positive entity, like positive quantity. So when can we take dQ positive? If at all the system gains heat energy from external source, or if we provide heat energy to the system like that. By any chance, if heat is lost from the system, or if the system loses its energy, then we people used to take dQ as negative. So this is the convention related to the first quantity, that is dQ. Exactly like that, if internal energy increases, then we people used to say du as positive, and if internal energy of the system decreases, then we say dQ value as negative. That is the convention as far as internal energy that is concerned, one should remember. And coming to this work done part of it, when work is done by the system, then we write dW as positive work. When work is done on the system, then automatically we take dW with a negative sign. That means this is as far as the convention of work done that is concerned. One should remember, these conventional signs will change the entire answer. If at all, by any chance, if we take a different, rather sign convention over there, or if sign convention varies over there, automatically you will get a different answer there. So one should be able to remember these 3 points as a convention that is required. Come to the last point over here, please. dQ is du plus dW. If you consider isothermal process, all of you can understand isothermal process in which temperature remains constant, but Q, the quantity of heat energy, which is variable over here. But all of us, we know very well, as long as the temperature remains constant, there will never be any change in the internal energy of the system. Therefore, du, the change in internal energy, will be 0 in isothermal process. Then how to write this equation now? dQ is equal to dW is equal to PdV. This is the way we people used to represent first law of thermodynamics for isothermal process as such. Now, if you take, for example, adiabatic process where you find temperature a variable, but of course we can understand the quantity of heat energy that remains constant. Means what? Neither the system takes heat energy from the external surroundings, nor the system releases heat energy to the external surroundings as such. So dQ is going to be 0 in this particular adiabatic process. Then how can we repeat this particular equation, please? dQ is 0 means you can directly write du plus dW is equal to 0. In other words, you can even write du is equal to minus dW, or vice versa. dW is equal to minus du. That is the way we people have to remember first law of thermodynamics for an adiabatic process as such. Come to the next one. That is, what is the equation for this isobaric process? Isobaric in the sense we can all understand pressure remains constant. There is no such rather term in this equation which gives you the change in pressure in the system. Therefore, dQ is equal to du plus dW equation can be taken as it is for any kind of isobaric process as such. That is a point you have to remember. Come down to the last one here, isochoric process. In fact, we know in this, volume remains constant. Volume remains constant means dV becomes 0. That in other words, work done will be 0. No work will be done in this particular isochoric process. Then how to write this equation? dQ is equal to du is the first law of thermodynamics for isochoric process. What is the meaning of that one? Whatever the supplied energy in the form of heat you people are finding, that energy simply increases the internal energy of the system as such. So these are the areas one should remember just before taking up the topic of this thermodynamics. In addition to that, we have the concept of a heat engine also, of which the eta value, that is what is called efficiency, it's 1 minus T2 by T1 in terms of temperatures of the source as well as the sink, right? In other words, 1 minus Q2 by Q1 we people used to take, where Q1 is the energy of the source and Q2 is that of the sink. So this actually is the formula for efficiency of a heat engine as such. So these are the areas which we people are taking up today in the form of different applications, please. Let us now check some of the questions of this thermodynamics chapter, please. Very first problem, two metal balls of same material having masses 50 gram and 100 gram collide with a target with the same velocity. That is the important most clue for this particular question. Same velocity, that is the point. Then the ratio of their rise in temperatures will be how much? In fact, we know W is equal to JH is the equation which we can take up. Now, metal ball is with the same velocity it is striking the target. That means half mv square will now be the work done. J into ms delta t or delta theta, that gives you the value of quantity of heat energy. But see carefully, mass gets cancelled. In addition to that, he has given two metal balls of the same material. Same material means what? Specific heat remains constant. Half anyhow is constant, we know. They are traveling with the same velocity. That means even velocity square also will be the same. Therefore, delta theta 1 is to delta theta 2 will definitely be 1:1, because we even know J is Joule's constant. Anyhow, it is a constant, we know. So, delta theta is going to be constant for each and every body. So, what should be your answer ultimately, please? 1:1. That means the fourth option is going to be the very correct option of this particular question number 1. Look at the second number, please. What is that question? Let us take up. Water falls from a height of 210 meter above the ground. Assuming that the surface on which the water is falling is perfectly insulated and all the energy of water is dissipated as heat, the rise in temperature of water is how much? Given the value of G as 10 meter per second square and Joule's constant 4200 Joule per kilocalorie, these are the values provided to us in the problem. Look at first of all once again, when water is falling, what kind of energy that water is going to have at that height? It will have potential energy, that is mgh. While coming down, that so-called potential energy will be converted into kinetic energy. That kinetic energy after reaching the surface of the ground will now be converted into heat energy over here. Means what? I directly can write mgh must be equal to J times ms delta T or delta theta. This is the equation what we can write. How much water that is falling is immaterial for us, because even though the mass is given in the problem, mass gets cancelled on both sides. What is our concentration now should be on? Delta theta is how much? It is GH by JS. That is the equation. But of course we know G is given as 10, fine. H is given as 210 meter. J is now 4.2. Observe very carefully here. J is 4.2 Joule per calorie. Therefore, S value whatever of water we people is to take, that of course S is going to be 1. You all know in fact S is 1 calorie per gram per degree centigrade. In other words, I can write this one 1000 calorie per kg per degree centigrade. That value I write it over here. That means 4.2 into 1000 is as well equivalent to 4200 only. That is the concept you need to understand here. This point and this 0 you can cut that one off. Two zeros they get cancelled over here, and of course this 21 goes in 42 2 times. So what will be the value of 1/2 now? It should be 0.5. What? Degree centigrade. Look at the options once again of this question number 2. 0.5 coincides with the second option that has been given over there. So automatically for this question number 2, second option, which is 0.5 degree centigrade, is the correct answer for us. Let us check the next number, problem number 3 please. A lead bullet strikes a steel target with a velocity of 300 meter per second and drops dead. It's a wonderful wording. Dropping dead means what? After striking, it is not moving further. That means no further energy that has been lost from the system as such. If the heat energy generated is shared equally between the bullet and the target, then the rise in temperature of the bullet is how much? Specific heat of lead is given 0.03 calorie per gram per degree centigrade as such. That is actually the concept. Now let us check once again. This also is based on the same formula. W is equal to JH. But in this particular example, that bullet is not falling from some height or something like. It is moving with certain velocity. Therefore, half mv square should now be taken as the work done by the bullet, which is equivalent to the kinetic energy of the bullet, is equal to J times ms delta T or delta theta, whatever you talk about. Once again, mass gets cancelled. Our concentration is on delta theta. But be a little careful with the wording what has been given. If the entire heat energy generated is shared equally between the bullet and the target, what is converted into heat energy here? Half mv square is converted into heat energy. Therefore, half of this one only is taken by the bullet. Therefore, half of half mv square is equal to j times ms delta theta. If I write delta theta now becomes v square by 4js. This is the concept we have to understand. What is the value of v given? 300 into 300 as it is you can go for. By 4 into j, I take it as usual as 4.2. What is 4.2? Joule per calorie. So, how to write S now? 0.03 into 1000 calorie per kg per degree centigrade. That now becomes simply 30. Now, you can cut this 0 and in fact, you can cut this 3 over here exactly 100 times. And of course, you can directly understand this 4 going here exactly 75 times. And if you take this 42 over here, once again 3, if you cut it over here, 25 times over here and here 14 times like. Now whatever the value, you will be getting 2500 by 14. That in other words, 1250, right, by 7. What is the value you people are getting over here? Directly, you will be getting 178.6. That is actually the concept what you people have to understand over here. That means what is important over here, just look at carefully. This half of half mv square, that is the concept because total energy is being shared. So one should understand that concept carefully, and calculation is not a bar. You directly can identify this equation, thereby you can substitute the values and find out the answer there, please. That is third question. The option is also 3 in this particular case, right? Let us check the next one, that is problem number 4. A steel drill, what he is talking about, you look at. A steel drill is making 180 rpm under constant couple of 5 Newton meter. If it drills a hole in 7 seconds in a steel block of mass 600 gram, the rise in temperature of the block is how much? In fact, when you are drilling something, due to the work what the drill is doing there, automatically heat will be generated. Due to this reason, some rise in temperature is going to be obtained or observed in that block as such. That's the value, of course, he is asking us to calculate. So once again, the formula remains the same. W is equal to JH only. But one should understand what is the value of work done which we have to take. We should take this one as torque into theta. In fact, W work is equal to force into linear displacement in linear dynamics part of it. If you take rotational dynamics concept over there, automatically their force here becomes a torque. Their displacement here becomes angular displacement theta. So tau theta is equal to J times ms delta theta, that is delta t. You can understand this one. What is this theta here? Theta is nothing other than angular displacement of this particular body as such. Remember, what are the values he has given you? Check now. 180 rpm. All of us, we know very well, when rpm to be converted into rps, we have to divide that one by 60. So it now becomes 3 rps. Then what will be the value of omega? It is 2 pi into 3, which now becomes 6 pi radian per second. That's the value of omega, and time is given 7 seconds. How much time it has taken to drill that one? Right, it is 7 seconds given. So what is the variation you should take in this particular equation, please? Tau times theta now can be written as omega t. Why? Because you can understand theta is equal to omega I into t plus half alpha t square formula officially. But here the drill is having a constant angular velocity. That means it will not have any angular acceleration as such. So this is equivalent to J times ms delta t. This is the formula. So what to write now under of this one, please? Totally we just want the value of delta t here. What is the delta t now? That is equal to tau times omega t divided by this value of j into m into S. What is the value of torque that is given? You look at, it's 5 Newton meter. Fine. What is omega? We have already calculated. It is 6 pi into time, that is given as 7. And J, if I take 4.2, what is the value of mass that is given here? 600 gram. You can write 0.6 gram, 0.6 kg. And what is the value of S? It's 0.1 calorie. 0.1 calorie, come on, convert that one into calorie per kg into 1000. Into 1000 means you will be getting exactly 100 there. Cut this point with these two zeros directly. This is 6 cancels over here directly, right? 7 cancels here over here 6 times. So directly what you are getting, 5 pi by 6, whatever this value you will be getting in degree centigrade, that you can take it as the temperature, the total value. 5 times pi means pi is 3.14. Around it is 15 odd. That means certainly your answer will be in the form of 2 point something. Around 2.6 degrees centigrade, you will be getting the rise in temperature of the system as such. So the option is going to be the very first option over here. Remember that. Let us check the next number, that is problem number 5 as such. Ratio of densities of two substances is 2:3 and that of specific heats is 1:2. The ratio of thermal capacities per unit volume respectively is how much? In fact, we all know very well, when we talk about thermal capacity, it is represented by this formula MS. But we can understand well, thermal capacity per unit volume we want. All of you can understand mass per unit volume is called density. So thermal capacity per unit volume, can't you write density into specific heat like please? So what we can write now? Q by V of the first substance divided by Q by V of the second substance. That's what has been asked over there. What is the ratio he is asking? That now becomes rho 1 by rho 2 into S1 by S2. Look at the ratio of densities given there. Densities are given 2:3. So write 2 by 3 into 1:2, that is the ratio of specific heats. 2 getting cancelled, 1 by 3 will be left. That means what is the correct ratio here please? 1:3. Look at that option number 3 please. It is exactly 1:3. We people also have got the same value over here. That is question number 5 as such. Look at the next number, that is problem number 6. The density of a substance is 400 kilogram kg per meter cube and that of another substance is 600 kg per meter cube. If you just look at these two values first of all, density of the first one, I take it as A. It is given something like 400 and of course kg per meter cube is the unit that has been mentioned. What about the second body? It is 600 kg per meter cube that has been mentioned as the density of the second one. The heat capacity of 40 cc of first substance is equal to that of 30 cc of the second substance. Means what? Q is equal to MS is the formula. Now you can even write this one as mass is equal to volume into density. If I write that one, V into rho into S I can write. Now the question is, his question is, the value of thermal capacities are equal of both the materials. Means what you can understand? VA rho A into SA must be equal to VB rho B into SB. If I consider A and B are the two substances what he is mentioning there. Now you can understand what is VA given. It is 40 cc, right, into what is rho A? It is 400 into SA, that in fact we do not know, is equal to how many cc of the second one he gave? 30 into what is the density of the second one? 600 into SB. You in fact can cut 200 twice here, thrice here. This 0 you can cut it off. Now what is left over? SA by SB we just want. 3 3s are 9 towards my right, 2 4 the 8, towards my left we are having. That in the sense SA by SB will now be 9:8. 9:8 means which is the correct option there? Third option is going to be the correct answer for this question number 6 as such. 9:8. Look at that third option. Now check the next problem. Problem number 7 please. Two liquids A and B are at 30 degrees centigrade and 20 degrees centigrade respectively. When they are mixed in equal masses, the temperature of the mixture is found to be 26 degrees centigrade. The ratio of their specific heats is how much? In fact, this is an application of the concept of method of mixtures. In fact, we all know what is this method of mixtures, what for it is being used. Method of mixtures, by using this one, we used to determine the values of specific heat capacities of different substances as such. Now look at in this case ms delta T, that is the heat lost by hot body, that is equal to heat gained by the cold body. Whether it is heat lost or heat gained, we have the same formula ms delta T. M for mass, S for specific heat, and delta T, it represents either rise in temperature of the body or loss in temperature of the body as such. Now look at for the first material please, Ma, right, into what is Sa we don't know, into what is the initial temperature of the first liquid. You see it is 30. Now it is becoming 26. Then 30 minus 26. Is it not temperature lost by hot body? That is going to be 4 degrees centigrade please. That is equal to Mb into Sb into the second body which was at 20 degrees centigrade, now rising up to 26 degrees centigrade. That means what will be the temperature gained by the second body? That is going to be 6. But in this case very clearly he has mentioned of equal masses they are mixed. Means what? Masses they get cancelled. So Sa by Sb, that is the ratio what we just want. It is 6 by 4 which now can be taken 3 by 2. That means what will be the correct ratio there please? 3:2. So which option is correct there? The fourth option 3:2 is going to be correct. So what one should understand for this model question is this. It is based on the method of mixtures of which the actual formula is heat lost by hot body is equal to heat gained by the cold body as such. Let us take the next problem. Problem 8. A beaker contains 200 grams of water. The heat capacity of the beaker is equal to that of 20 gram water. The initial temperature of water in the beaker is 20 degrees centigrade. If 440 gram of hot water at 92 degrees centigrade is poured in, the final temperature will be nearly. Look at the wording carefully. What is losing heat energy here? Hot water is losing heat energy. What is gaining heat energy here? It is the beaker and the water in the beaker, both of course are gaining heat energy. So what we should understand here, ms delta T of hot water, that means you can take this one for granted, it is heat lost by hot water is equal to ms delta T of the beaker, that in the sense heat is gained by the beaker, plus ms delta T of that cold water, whatever was inside the beaker right from the very beginning. So what we should understand, how much hot water is added to the system? 440 grams of hot water is added. But we know pretty well when we are taking the values in CGS units, straight away S can be taken as 1. Now, hot water's temperature was 92. It's now coming down to some other value. Let us take that value as T. That means from 92 degrees, hot water has come down to the temperature, say T degrees. Now this is equal to, what is the thermal capacity of the beaker given please? It is 20 gram of water he has given. So 20 into, what are the original temperature of beaker given? 20. It is now going up to T. Therefore, T minus 20 I can write. So that is the rise in temperature of this particular beaker as such. Plus, how much water was there earlier? 200 into this value of SS1 once again, whatever is the rise in temperature of this beaker, same will be the rise in temperature of this particular water in the beaker also. In this entire equation, there is only one quantity which is not known to us, that itself is the value of T there. Now if you cut this 20 here, here 10 times, here 22 times, then what will be the equation? 22 times 92 minus 22T is equal to T minus 20 minus 10T minus 200. That of course you can understand T minus 20, it's okay, plus 10T minus 200. So what you will be getting here, if it is goes over there onto the other side, 32T, this of course 10 plus 1, 11T here, 11 plus 22, it is now 33T is equal to how much? 22 into 92, right, plus 220. That in the sense I can write 22 into 10 also. So 22 if I take common into 102, I can directly write that by 33 will now be the temperature of the system. Now if you look at this one directly, 2 times 11, 3 times over here, this goes 34 times. So exactly 68 degrees centigrade will now be the rise in temperature of the system. So 68 means the second option that is tallied there. So this is the method we people have to adopt whenever we use the concept of method of mixes to calculate specific heat or rise in temperature, whatever it is. Now check the very next problem please. Problem number 9. 1 gram of ice at 0 degrees centigrade is added to 5 gram of water at 10 degrees centigrade. If the latent heat of ice be 80 calorie per gram, then the final temperature of the mixture will be how much? In these model questions, you in fact need not work out much. A bit of observation will make you get the answer directly. 1 gram he is talking about ice. And what is it mixed with? It is given 5 gram of water, which initially was at a temperature say 10 degrees centigrade. Fine. Now look at carefully. For ice to melt, for every 1 gram of ice to melt, we require 80 calories of heat. That means we can understand it requires simply 1 into 80. That means 80 calories of heat it requires just to melt. And we know pretty well, unless the entire ice is completely melted, we will not find the change in its temperature. Temperature of ice will remain at 0 degrees only until unless the entire ice is completely and totally converted into water. That's the point. Now how much energy this water can provide this one? It can provide ms delta T of energy. How much is m? 5. S is 1. Delta T is 10. That means how much energy it can provide to this ice? After all 50 calories. How much it requires to melt? 80 calories. That means it is unable to give the amount whatever is required by this ice. That means what is clear here? The temperature of ice will not be changed unless it gets some energy which is more than 80 calories over here. But here how much energy it is giving? Only 50. Therefore the temperature will remain the same. Means the temperature will be at 0 degrees centigrade only. The second option is going to be the correct option for this. So in such models, you need not directly equate the values and all. Understand directly how much that requires, how much this can provide. Looking to these two, you can finalize your answer at Eamcet level very easily. That is question number 9. The correct option for this one is going to be the second option there. Look at the next number, that is question number 10. The amount of heat required to convert 1 gram of ice at minus 10 degrees centigrade into steam at 100 degrees centigrade is how much? This particular type of a question needs some understanding in the sense we are having 1 gram of ice. 1 gram of ice, okay. How much? What is the temperature? It is earlier at minus 10 degrees centigrade. Imagine for a while, I have taken 1 gram of ice which is at minus 10 degrees centigrade into a beaker. I have started heating the beaker till the entire ice is completely converted into steam. Till that extent, I don't want to stop giving heat energy to the system. So what are the changes you are going to find first of all? Temperature of ice will now increase first of all to 0 degrees. Of course, basic knowledge over here says minus 10 degrees, if it increases, it becomes minus 9, minus 8, minus 7, like that it comes to 0. Till it comes to 0, ice will be as ice only. You know very well, ice will be formed at 0 degrees centigrade only. This is the first stage. When I still give heat energy to the system, ice now melts into water. But this melting of ice takes place at a constant temperature which is called melting point of ice. What is that value? 0 degrees. So temperature will not change now, but the state of this particular ice will now be converted into water over here. That is the understanding. Now come to the next one. If I heat it up further, this temperature of water will now rise up to 100 degrees centigrade. That is our third step. Followed. Then if I give further heat energy to the system, water will now be converted into steam, but temperature will remain 100 degrees centigrade only. So carefully if you observe, the conversion of ice at minus 10 degrees centigrade into steam at 100 degrees centigrade, that requires 4 different stages. In the first stage, temperature of ice must be increased from minus 10 to 0. In the second stage, ice will be converted into water at 0 degrees centigrade. In the third stage, temperature of water rises from 0 to 100 degrees centigrade. In the fourth stage, at the same constant temperature which is called boiling point of water, this water is converted into steam. In all these 4 stages, how much quantity of heat energy we are supplying to the system? Let us take that one. Q1 is the heat energy supplied in the first stage. That I should write ms delta T. Why it is to be written like that also you can understand. Change in temperature is observed. Therefore, ms delta T. S is of what? Ice I should take. What is mass given? 1. What is the value of S of ice please? Half. 0.5. And what will be the temperature rise? It is 10. So how many calories we people are getting here? 5 calories. Means what? 5 calories of heat if I supply, that minus 10 degrees centigrade of ice will now come up to 0 degrees centigrade of ice. Now the second quantity of heat energy where the change of state is taking place, I should write ml. That L stands for latent heat, and all of you know this latent heat is of ice. Mass is 1 gram and 80 calories is the value over here. So how many calories it requires to convert into water? 80 calories. In the third stage, if I write Q3, once again I should take ms delta T. This time S is of water please. Because M is 1 here, S is 1 here, rise in temperature is 100 here, therefore 100 calories of heat energy that is needed to be given to the system over here. Now in the fourth stage, Q4 now becomes ml, because once again it is change of state that is taking place. L of what? The steam value we should take, and its value is 540. So 1 into 540, how much it will be? 540 calories. Now look at carefully, 540 plus 100 plus 80 plus 5. It is 540 plus 100, 640, 720 and 725. That actually is so many calories, that much of heat energy that is really required. But unfortunately, 725 calories I have got the answer, but all the options are given in joule. One should understand immediately 725 calories we have to convert them into joules. Now 1 calorie is equal to 4.2 joule. Remember that result. 1 calorie is equal to 4.2 joule. Then 725 calories how much? Into 4.2. Whatever the value you people are getting now, that will now be 3045 joules you will be getting exactly for this. So how many joules of energy that is needed for this entire conversion, you people can understand. That means one has to remember like this. If they ask the answer in calories, fine. Otherwise they can ask you in joule. Sometimes they may ask you in electron volt. That time of course 1 electron volt is 1.6 into 10 power minus 19. So after getting the value in joule, you should divide this one by 1.6 into 10 power power minus 19. Then you will be getting the answer in electron volts and so on like that. So that is question number 10, for which the option is the very first one, please, 3045 joule. Let us check the next question, that is problem number 11. Three liquids A, B and C of masses 400 gram, 600 gram, 800 gram are at 30 degrees centigrade, 40 degrees centigrade and 50 degrees centigrade respectively. When A and B are mixed, the resultant temperature is 36 degrees centigrade. When B and C are mixed, resultant temperature is 44. Then the ratio of their specific heats is how much? That is the concept. Here, three different liquids he is talking about. Let us check first of all. You take A, you take B, you take C. The very first one is of 400 gram he gave, and second one is given 600 gram, and third one is given 800 gram. So these are the masses given, fine. Now initially the first one is at 30 degrees centigrade, the second one is at 40 degrees centigrade, and the third one is at 50 degrees centigrade. These are the values they have provided us. Now when A and B are mixed, then what is happening? The resultant temperature has become 36 degrees. Means what you should understand? 30 degrees of A is increasing to 36, whereas 40 degrees of B is coming down to 36. That means A is gaining heat energy, B is losing heat energy. How to write this equation? MA into SA into delta theta is equal to MB into SB into delta theta. Here it is rise in temperature, here it is loss in temperature. This is theta 1, you take this theta 2, you take for example. This now becomes 400 into SA into what is rise in temperature? 6. What is MB? 600 into what is specific heat? We don't know. That into loss of temperature here will be 4 degrees now. Now look at carefully, 600 into 4 is 2400. 400 into 6 also is 2400. So what is it you are getting from this one? SA is equal to SB. That means first one and second one have got the same value of specific heats. Now when B and C are mixed, what is the value he has given you? 44 degrees is the resultant temperature. That means this is gaining, this is losing. How to write that corresponding equation now, please? You can take 600 into SB into the rise in temperature is 4. That is equal to 800 into SC into the loss in temperature will be 6. Now you can cut 100 if you take for example 6 times here and these two zeros of course 8 times here. Now what next we can cut? 6 cancels on both sides. Then SB by SC, or directly also you can write SB by SC is equal to this 8 by 4 you are getting. That means it is 2. So you can understand well, SB is equal to 2SC. That is the point. Now you write the same step here. SA is to, SB is to, SC we want. SA, you write it as it is. SB also is equal to SA. That is also same. Then what is SC? SB by 2. That also can be written SA by 2. Come and take the ratio please. 2 is to 2 is to 1. So what will be the corresponding ratio of specific heats please? 2 is to 2 is to 1 means the third option is going to be the right and correct option for this question number 11. So that is a point you have to remember for this question number 11 please. Let us check the very next problem, that is problem number 12 as such. What is that one? Let us read. A quantity of heat Q is supplied to a monoatomic ideal gas which expands at constant pressure. The fraction of heat that goes into work done by the gas is how much? Fraction of heat that goes into work done, that means dW by dQ. That is what we want. In fact, dW can be written as nR dt by dQ can be written as ncp dt. You can understand well when n and dt they get cancelled. Cp minus Cv by Cp I can write. It is 1 minus 1 by gamma. This is actually the case. 1 minus 1 by what kind of a gas that has been mentioned? Monoatomic. For monoatomic, gamma is 5 by 3. Then what to write this 5 by 3? How to write that one? 5 by 3, when I write it here, 1 minus 3 by 5 I will get. That 5 minus 3 will be how much now? 2 by 5. This is the fraction of that amount of heat energy which is converted into work done. So what is the correct option over here, please? Very first option, which is 2 by 5. That is now going to be the fractional energy which is utilized to do some work by the gas, like that is a concept. Look at the next problem, problem number 13. 70 calories of heat is required to rise the temperature of 2 moles of an ideal gas at constant pressure from 25 degrees centigrade to 30 degrees centigrade. First and foremost, see the wording carefully. At constant pressure he is talking. That means Q can be written as, right, NCP dt. That is the formula, because it's constant pressure he is talking. What is Q given? 70. How many moles of the gas he has given? 2 moles into Cp. We don't know the value. What is the rise in temperature? 25 to 30. So the variation will be 5. Therefore, what will I get? Cp is equal to 7 units directly I will be getting. Right? Of course, it is Cp means specific heat at constant pressure. Calorie per gram per degree centigrade or calorie per mole per degree centigrade in this case. We people can write like that. What is the question that is asked? Amount of heat required to rise the temperature of the same gas through the same rise of temperature at constant volume. That means Q1 I just want, which is NCV dt now. But N will be once again 2 only. How to write Cv now? Cp minus Cv is equal to R. Then automatically Cv can be written as Cp minus R. I write Cp minus R into delta T will be same as before. It is 5 only. But you know very well 2 into 5 here. Okay. What is Cp? 7. What is the value of R in CGS? 2. Then what is the difference here? 5 5 is 25 times 2, which now will be 50. So how many calories of heat that is required at constant volume for us? 50 calories that is required. That in the sense the very first option, that's going to be true for this question number 13 as such. So NCV dt at constant pressure, NCP dt at constant pressure, NCV dt at constant volume we people used to take up. Now let us check the next problem, problem number 14 this time. In a thermodynamic process with 2 moles of gas, 30 joule of heat is released and 22 joule of work is done on the gas. Given that the initial internal energy of the sample is 20 joule, then the final internal energy will be how much? This is a direct application of first law of thermodynamics, please. dq is equal to du plus dw. That is the concept. du can be written u final minus u initial. That is final internal energy minus initial internal energy plus dw is equal to dq. Fine. But one should remember the convention carefully, I said. Look at first. 30 joule of heat is released. Released means what? That value of 30 should be taken with a negative sign. If it is gaining the heat energy, we should write with positive sign. That is one point. 22 joule of work is done on the gas. On the gas means that value is to be taken negative once again, 22. Okay. Now what is U final is the question. What is the initial internal energy that is of the sample given? It is 20. Now look at carefully here, please. This now becomes U final minus 42 is equal to minus 30. So U final will be how much? 42 minus 30, which now becomes 12 watt. Whatever the units he has given you as joule must now be the corresponding answer. So what is the correct option for this question number 14, please? It is fourth option, 12 joule. That is the case. By mistake, if you have not taken this negative sign or this negative sign, you definitely will be getting some other option which has been provided in 1, 2 and 3 options, third options of that particular question, please. So be careful and thorough with this convention. Now coming to question number 15, the very next number over here, please. Look at. For a gas, the ratio of specific heats at constant pressure to the specific heat at constant volume is 5/3. That gamma value is given 5/3. That's one value he is providing us. 800 cc of this gas is suddenly compressed to 100 cc. If the initial pressure is P, then the final pressure is. One thing you people can understand, the moment gamma value is provided, it is understood the particular process of compression is taking place in terms of adiabatic process. So what to write? P1 V1 to the power gamma is equal to P2 V2 to the power gamma. I can write that in the sense P1 by P2 is equal to V2 by V1 whole to the power gamma. What is the initial volume that is given? 800 cc. What is the final volume that has been given? 100 cc. Now you can take this one as 100 by 800. That of course whole power gamma, it is 5/3. Now this becomes 1/8. Cube root of 1/8 is 1/2. So it now becomes 1/32. So what will now be the value of P2 please? It should now be 32 times P1. So how many times it increases now? 32 times it should increase. The correct option for this one is the fourth option. So one should remember this equation as far as Boyle's law that is concerned for adiabatic process. Look at the next number this time. 2 moles of a monoatomic gas of gamma 5/3 is mixed with 3 moles of a diatomic gas of gamma 7/5. Then the value of gamma of the mixture is how much? This is a very commonly asked model at Eamcet examination please. Gamma of the mixture we just want. That is N1 Cp1 plus N2 Cp2 divided by N1 Cv1 plus N2 Cv2. That is the direct formula one can remember in this case please. But all of you can understand N1, how many moles? 2 moles of monoatomic gas. Monoatomic gas, what is the value of Cp? It is 5R/2 plus, what is the second one here? 3 moles of a diatomic gas. What is Cp for diatomic gas? 7R/2 divided by 2 into, what is Cv for monoatomic gas? 3R/2. What is the value of Cv for diatomic gas? 5R/2. So automatically if you simplify this whole lot, you will be getting near around 1.5. That is the corresponding answer. Means what? The third option is going to be the correct option for this particular question number 16 as such. But remember this formula for the mixture, not only 2 gases, any number of gases, let them join or mix them up. You will be finding this kind of a formula for that. That is the concept we have to take. Now let us check the very next problem please. That is problem number 17 please. 1 mole of an ideal gas gamma 7/5 is adiabatically compressed so that its temperature changes from 27 degrees centigrade to 35 degrees centigrade. What is the work done by the gas? Work done in this particular case is NCV dt officially. But of course we people can write it like this also, N into R by gamma minus 1 into dt. Of course we know very well how many moles he has given, 1 mole. R of course he has given 8.4, fine. What is the other value given? Gamma, he is telling us 7/5 minus 1, that is the value. Into what is the variation in temperature you are finding? 27 to 35, it now will be simply 8. Now whatever the value here you get, 7/5 minus 1 means how much it will be? 2/5. So 5 goes up. So 5 times 8.4 into 8. 8 8 is 64 generally, right? This in what way this is 5 times means what? 7 minus 5/2 also you will be having. So this now becomes, this goes 4 times. So 20 into 84, 8.4. That point and this 0 if you cut it off, you will be getting how much? Around 168 exactly. With a negative sign. What for this negative sign? In fact, very clearly you can understand that one. It has been compressed, means we people are doing the work on the system. If the system does the work by itself, that work done is to be taken positive, otherwise it should be taken negative. I have already told you. So it should now be written minus 168 joule. The second option is the correct option for this question number 17, please. Look at the next number, that is 18. During an adiabatic process, the pressure of a gas is proportional to the cube of its absolute temperature. The value of Cp by Cv for that gas is how much? One thing one should understand here, pressure is proportional to cube of the absolute temperature. In other words, I can write P by T cube as constant. In other words, I can even write P into T power minus 3 is constant. That is the case officially. But we know pretty well P to the power 1 minus gamma into T power gamma is constant, is the relation between P and T when we consider an adiabatic process. Then how to rewrite this one now? P into T power gamma by 1 minus gamma is equal to constant, I can write directly. Now just compare this given equation and this known equation, please. P is common, T power minus 3 over there, here is T power gamma minus 1. So I can write gamma by 1 minus gamma must be equal to minus 3. That is the relation between these two. What is the value of gamma? Of course, we people have to take up. What is gamma? The question. So you can take gamma is equal to minus 3 plus 3 gamma. So this gamma going there, 2 gamma is equal to 3. Then gamma automatically will be 3 by 2 as such. So what is going to be the correct option for this question? Question number 18, the correct option is the fourth option, that is 3 by 2. So let us check the next problem, that is question number 19. Same question has been asked in one of the Eamcet examinations in the previous years. See that question carefully. The samples of the same gas X, Y and Z for which the ratio of specific heats is 3 by 2 have initially the same volume. What are the things he is giving? X, Y and Z like this. And what did he say? The volume of each sample is doubled by adiabatic process in the case of X. For X it is adiabatic process. Adiabatic process means one should take P1 V1 to the power gamma is equal to P2 V2 to the power gamma. Now his concept is what? Volume is doubled. Then I can directly write this way, P1 by P2 is equal to V2 by V1 whole power gamma I can write. Then what is V2? It is 2V1 by V1 whole power gamma. So what will be this value now? 2 to the power, what is gamma given? 3 by 2. That means root 2 whole cube. Root 2 whole cube, is it not root 2 root 2 please? So what we can write now? P2 is equal to P1 by 2 root 2. This is the value of final pressure of the first sample that has been taken. Right? See the second one please. In the case of Y, it is taken in as isothermal process in the case of Z and isobaric for Y. You can all understand well isobaric. When I consider isobaric, pressure 1 and pressure 2 are supposed to be equal. Isobaric itself means no change in pressure system. So P2 will now be equal to P1 itself. That is the point you have to understand. And what about Z? Isothermal like it has been expanded. Isothermal means what is to be taken? P1 V1 is equal to P2 V2. Then what will be P2? It is P1 V1 by V2. You can certainly understand it is P1 into, right? V1 by 2V1. V1 getting cancelled. What is left over? P1 by 2 you will be getting as P2. But the point in this particular case is this is 2 root 2, that is P1 by 2, this is P like. What are the ratios of their final values? And he has given you the pressures of the values are 2 root 2 is to 1 is to 2. If the pressure is 2 root 2, 2 root 2 by 2 root 2. What will be this value? 1. This is 1 by 1. That means P2 is equal to 1 here. And the second one, P1 is 2 he has given. 2 by 2. That is again 1 here. So here P2 is 1. Here also 1. Here also 1. Therefore, what is the ratio of their final pressures? It will be 1:1:1. So all the three different processes he is talking about, but option is going to be 1:1:1. That second option is going to be the correct answer for this question number 19, one of the very, very interesting models of this particular chapter. Let us check the next one, that is question number 20. An ideal engine whose efficiency is 40% receives heat at 500 Kelvin. If the efficiency is to be 50%, the temperature of the sink will be how much? In fact, this is a direct application of heat engine. The efficiency, of course, has been given how much in the first case? 40% it is given. 40% is equal to what? 1 minus that value of T2 by T1. T2 by 500, because it is taking 500 energy there. So what can we write? T2 by 500 is equal to 1 minus 40 by 100, which now becomes 60 by 100 as such. You can cut these two zeros as such. T2 now becomes 300 Kelvin. That is the temperature of what? The sink. We have got 300 Kelvin. Now the question is, what should be the temperature of the sink when the efficiency to become 50%? So you write 50% this time. That is equal to 1 minus T2 by again T1. That is 500. What will be the value of T2 by 500 this time again? It is 1 minus 50 by 100, which now becomes 50 by 100 as such. Come on, cut these two zeros. What will be the value of T2 now? It is just 250 Kelvin, like you can understand. So in this particular question, he is simply asking you what is this value. Otherwise, he can even ask you what is the ratio of these temperatures of the sink in both the cases, like that also. But in this case, no need for you to take the ratio. Fourth option is going to be the very correct option for this particular question as such, right? So if you take up the concept over here, these are the models whatever we people are having as far as thermodynamics part that is concerned. One of the very, very important chapters of heat, right? And thermodynamics, in one way you can think of 1 to 2 questions are expected from this particular thermodynamics itself. So if you are thorough with this, I'm sure that every one of you can just bag 2 marks as a minimum as such. In the next class, of course, we are going to discuss about the last chapter of heat, which of course is the transmission of heat, in which we are taking up conduction, convection and radiation part of heat energy as such, right? I hope all of you might have understood this topic. Thank you.